Guys, today we're going to be learning laws of motion under 30 minutes. Yes, you heard it right. Laws of motion under 30 minutes max. So here we're having an Akash module and we're going to just study the basic concepts, okay? Basic concepts and formulas, which is very, very important for solving, okay? All the pulley formulas and all that stuff. So let us start, right? And we'll start with Aristotle's fallacy. Okay, here you can see Aristotle's fallacy. So what was Aristotle's fallacy? What did he say? Right, that is some curiosity that we have. What did this guy say? So Aristotle was a Greek philosopher, and he said that a force a force was required to keep a body in motion. What did he say? He said that the force was required to keep a body in motion, right? And he said that if a motion had no force, it would just stop. Okay, so what he said that the body had to keep moving. Something external was required, some external force was required, right? And he said that this arrow, if it was fired from a bow, if an arrow was fired from a bow, it would keep moving, right? It would keep moving. So why would it keep moving? If an arrow was fired from a bow, it could keep moving. He said that the air from behind the arrow would push the arrow forward. That is why even after you fire, this is a bow, right? Imagine this is a bow. Even after you fire an arrow from a bow, it will keep moving, because he said that the air from behind the arrow will push the arrow, which is absolutely wrong. So Aristotle's fallacy is wrong. Okay, he said, basically, let's prove it in statements. An external force is required to keep a body in motion. Is required to keep a body in motion. Okay, this is what he said. Now we'll learn about, just to disprove it, we'll learn about law of inertia. Okay, who gave this law? Who gave the law of inertia? A person called Galileo. Okay, basically we're not going to focus on that much theory today. Not much theory. Okay, theory is less, more formulas. Okay, and we're going to solve some numericals as well. Okay, some easy numericals. So Galileo, okay, this guy, I don't know what's his spelling, okay, don't blame me. So he was the one who explained the law of inertia. So what did he do? He took a triangular thing. Okay, he took a triangular, whatever this might be, you can call it an inclined plane. Okay, you'll call it an inclined plane. He took a triangular inclined plane and he let a ball fly from it. So its initial velocity will be u, final velocity will be v, right? Now as it rolls down, the speed will increase, right? Why will the speed increase? See, it is moving towards gravity, right? So the speed will keep increasing. So the speed will keep increasing as it rolls down. But now again we'll take the same case of an inclined plane, but instead of, now we're going to take a inclined plane and we're going to let a ball move upwards. See, for example, when you're climbing downstairs, you will feel energetic. Will you feel tired? No, you can do it faster, right? But when you're climbing upstairs, you'll feel tired, right? Same thing here also. The ball will have, the speed of the ball will decrease, right? So speed, this is v, speed decreases. Okay, done. Speed decreases. So what should happen if it was kept on a horizontal plane? Now what should happen? See, what should happen if a ball was kept on a horizontal plane? See, the speed of the ball should be constant, right? Speed should be constant. So now why should it be constant? See, if you made it go from up to down, it would increase, speed would increase. If you made it go from down to, if you made it go from down to up, if you made it go from down to up, speed would decrease. So if it was just in a horizontal plane, it should not increase also, not decrease also. That means it should remain constant. It should remain constant. But there is an opposing force. What is this force? This force is friction. This force is called frictional force. So if there was a smooth plane, this ball would keep moving endlessly. Why would it keep moving endlessly? to reach, see, if it was dropped from an inclined plane, if it was dropped from an inclined plane, it has to cover this height, right? To cover this height, it would keep moving, but sadly we cannot have a frictionless surface, right? Because there is some sort of friction, there is some sort of friction which will slow down the speed of the ball, right? And finally it will become zero. So that was law of inertia. What is law of inertia? Law of inertia is the tendency of the object to remain in its state of rest or in uh, constant velocity, to move with constant velocity. Okay. Now this is a Bob pendulum case. We do not need to study this, but basically the conclusion we'll see. Okay. Now, so Galileo arrived at a new insight of motion that excluded Aristotle and those who followed him. So Aristotle was wrong. What did this Galileo say? He said that a body at rest continues to remain at rest, and a body at motion continues to move with uniform velocity. This property is known as inertia. So body at rest will continue to remain in rest, okay, and body in motion will continue to remain in motion unless an external force is acted upon by the body. Okay, so that is what we understood. Now system and external force. Okay, a system may be consistent with a single particle. Okay, so a system may be consistent with a single particle block or a combination of two blocks kept over each other as piece of string. All of this system should have a same acceleration. For example, we'll suspend two blocks on the pulley. So this whole thing is called a system. Okay, and their acceleration should be the same. Acceleration should be the same if it's like this. If it's at the same distance, like one is not up, one is not down, right? They have the same weight, so acceleration should be the same. um, any force inside the system of the body, see, any force inside the system from the bodies outside the system. Okay, wait, outside force, we're only considering outside force. Okay, we are not considering the inside forces of the system. Fine. Fine. Now we'll study about Newton's first law of motion. What are we going to study about? Newton's first law of motion. We have learned this, right? We have learned this in 9th standard, so it's going to be pretty easy. Okay. So basically, what is it? Newton built on Galileo's ideas, and every body continues to be in its state of rest or uniform motion in a straight line unless compelled by some external force to act otherwise. So what did he say? We have to remember this statement for our boards. Every body continues to remain in its state of rest or uniform motion. Okay, it will be at rest or in uniform motion unless compelled to change that state. Unless compelled to change that state. Okay, that state. Okay, that is basically Newton's first law. Now we'll be learning about inertia and mass. Okay, inertia and mass. Inertia and mass. What is inertia and mass? What is this? See, consider bodies of unequal masses. Say a tennis ball. This is a tennis ball, size of tennis ball approximate. Okay, this is how a tennis ball looks like. I guess I don't remember. And this is the size of a cricket ball. Okay, wait, not that. It's a bit bigger, right? Okay, maybe this much. Okay, this is the size of a cricket ball. This is a tennis ball and this is a cricket ball. Now which will fall faster? I mean, wait. So which has more velocity? Obviously you will say tennis ball will fall faster, right? So the velocity of the tennis ball will be greater than the cricket ball. So who has more inertia? See, inertia is the tendency of the body to remain in a state of rest, right? Both were at rest at the start. Which remained in its state of rest more? This, right? This opposed, it came late. So it has more inertia because it remained in its state of rest. What is inertia? The tendency of a body to remain in its state of rest or uniform motion. Since it was at rest, it will be at rest only. It will move slowly, right? So it has more inertia. Okay, so what should we understand from this? We should understand that inertia is directly proportional to the mass of the body. Okay, if a body is heavier, it will have more inertia. Fine. See, I'll give you another example. Here is a here is a bicycle. Okay, just imagine this is a bicycle and this is you. What do you do? See, the bicycle. Okay, this is not you. This is a tree. For example, let's imagine it's a tree and there is no person on the bicycle. The bicycle hits the tree. What will happen to the tree? Nothing much will happen, right? Nothing much will happen to the tree. But let us imagine that a huge truck will hit the same tree. What will happen? What will happen? Can we see if a bicycle hits the tree, it can stop. Will the truck stop? If it is moving with a high speed, will it stop? No. It's difficult for the truck to stop, right? And even the tree will get damaged. Okay, we learn about that momentum and all that, impulsive forces. We learn, this is just a simple example just for you to think about it. Inertia and its types. There are three types of inertia which you need to learn. I'll give one example of each. Inertia of rest, first one. Inertia of motion, second one. Inertia of motion and inertia of direction. Inertia of rest, inertia of motion, inertia of direction. Okay, we'll give example for each of them and we'll complete inertia. Okay, then we'll move on to the second law. See, inertia of rest. It is the inability of a body of its virtue which it cannot move by itself. Okay, so for example, a simple example. Okay, inertia of rest. We're giving an example for inertia of rest. For example, there is a bus. There is a bus, and you are sitting in the bus. You're sitting in the bus. Okay, you're sitting in the bus. Now what happens is, you're just sitting normally, you're at rest, all your passengers are at rest. Suddenly the bus starts moving. Suddenly the bus starts moving. Will you fall backward or will you fall forward? Imagine the situation. You're sitting, bus starts moving suddenly. Will you fall backward or forward? Yes, you will fall forward. Okay, you'll fall forward. No? Then you'll fall backwards, right? You'll fall backwards. Why will you fall backwards? Why will you go backwards? See, basically, when you're at rest, the whole upper portion of your body is at rest, right? But when the bus starts moving, suddenly the feet is in contact with the bus. It is in motion. Your body is at rest. Your feet is in motion. Okay, that is so weird. Your body is still at rest, but your feet is in motion. So it is going, but your body falls backwards because it's still at rest, right? So it falls backwards. So this is an example of inertia of rest. Okay, one example is given of inertia of rest. We'll move on to inertia of motion. Inertia of motion. So what is inertia of motion? What is inertia of motion? Same case, bus case. But this time you're standing on the bus, whatever, sitting, standing, whatever. Okay, you're just standing and it's moving. Okay, you're holding onto the bus. You're standing, like with your friends, you're talking, cha cha cha, and the bus is moving. And suddenly the driver decides to put a brake. Okay, so the bus stopped. What will happen to you? Will you fall forward or backward? You'll fall forward, right? You'll fall forward. Why will you fall forward? What is the reason for you for falling forward? See, basically, first your feet is in motion, right? But it is in contact with the bus, so when the bus brakes, even your feet is at rest, it becomes at rest, but your body, it is still in inertia, it is still in motion. So what will happen? You will fall forward, you will fall. Okay, then the last one is inertia of direction. We learn about inertia of direction, we can move to the second law. Inertia of direction. Okay, a simple example can be given for this. For example, you're sitting in a car. Okay, all this boring examples. Okay, car examples only. You're sitting in a car. That's a weird car. Don't mind. Okay, and you're just moving in a straight road. Just moving in a straight road. Okay, suddenly when you turn to one side. Okay, suddenly see, you're moving like this. Suddenly you turn to this side. For example, where will you fall? Wait, you're moving this side. Okay, you're sitting this side. It's moving straight, it'll turn this side. Which side will you fall? You'll fall to this side, right? You won't fall this side only. It's turning this side, you'll fall this side. Why is that so? See, you are moving straight, your body is at inertia, so it'll keep moving straight. But your feet, like the whole car will move this side. So you'll still be in the straight position itself. Right? See, you're like this, okay? And the direction is changing, but still you're like this only. So what'll happen? You'll move like this. right? Okay, that is inertia of direction. The three inertias are done. Okay, now moving on, some examples. One example will say, when we shake the branches of the tree, the fruits fall down due to inertia of rest. See, when you're shaking the branches of a tree, the whole tree is in motion, but the fruits are still at rest due to inertia, so it falls down. Okay, just like an apple falling from a tree. Now, okay, these are just some questions. We'll skip that and we'll go on to momentum. Momentum is an important quantity. Momentum. So, what is this momentum? What is this momentum? Basically, it is defined as the quantity of motion contained in a body. It is measured as the product of mass and velocity. So, momentum is mass and velocity of the body, right? It is represented by P. We know that P is equal to mv. To understand this, let's have two cases. We'll understand this with the example of a case. We'll understand this with the example of a case. Case 1. Okay. Now there is a ball of mass 1 gram. Okay, and it's moving with the velocity. It's moving with certain velocity. Okay, it's not given here. It's moving with certain velocity. Can you stop it? Can you stop it? Of course you can stop it, right? You can stop the ball. But what if a body is moving with velocity 0.1? Can you stop it? Yes, of course you can stop it. But what if it is a train? What if it is a huge train? Can you stop it then? Can you stop it then? Not 0.01, 0.1. Yes, now it will make you think for a bit, right? That is momentum. From these two cases, it's clear that having a knowledge of one quantity, either mass or velocity, cannot tell how much motion is contained in a body. If you know the mass, you cannot tell, okay, it will come at this much motion, it will come at this much. And if you know the speed also, you cannot tell how much will be the, whether you can stop it or not. So hence we require a term which contains both mass and velocity, which is, yes, our momentum, which is our momentum. These examples indicate the importance of this quantity. So from P is equal to m into v. Velocity is vector, momentum is vector. When mass is constant, what is the meaning of mass is constant? That means it does not change. When mass is constant, then P is directly proportional to V, right? So if you plot a graph of, here V will be there, here P. If you plot a graph of this, it will be a straight line since they're directly proportional. Okay, again, if you plot a graph, if the velocity of the body is constant, this time the velocity is constant. The velocity is constant. If velocity is constant, if you plot a graph between, see, if velocity is constant, momentum is directly proportional to mass, right? So if you plot a graph between P and M, it will be straight. Okay, whenever it is directly proportional, it's a straight line. And then one more last case we have. When two bodies of unequal masses have equal momentum, then their v varies inversely as shown. See, now two bodies are there. They have different masses. Okay, they have different masses. Let's make a huge body. There are two bodies, they have different masses. Okay, and they have equal momentum. Momentum is equal momentum. And their velocity varies inversely as their masses. Okay, velocity varies inversely. That means the smaller one will have greater velocity, right? And the bigger one will have lesser velocity. Okay, smaller one will have greater velocity, bigger one will have smaller velocity. So velocity varies inversely, they're saying. And they have unequal, okay, they have equal momentum. Sorry, they have equal momentum but different masses. Then what should we do? V1 by V2. Since it varies inversely, velocity varies inversely, you have to do m2 by m1, right? Because see, a huge mass will have less velocity, a small mass will have more velocity. So now if you plot a graph between this, if it is inverse, right? If it is inverse, you will get a hyperbola. This is a hyperbola, means graph like this. Okay, this is a hyperbolic graph. It can be like any shape. Okay, basically you'll get this hyperbola. That's it. You'll get this hyperbola. Okay, the momentum is constant. They have only given no equal momentum, so momentum is constant. Okay, done. Now we're moving on to force. See, now one example is given here, okay? Suppose you catch a cricket ball and a tennis ball which is dropped from the same height. We find that it's easier to catch a tennis ball than a cricket ball because cricket ball has more mass. This determined mass is an important factor that determines the effect of force in its motion. So finally we're coming to force. When we look around us, we observe a state of rest of motion of bodies. We find that nothing moves on its own. Right? Nothing moves on its own. When we push or pull a body, it may change the state of rest or uniform motion. So when we apply force we can cause a body to move, right? Or we can stop a body, right? So it can cause change in its state of motion, whether it is rest or uniform motion. It may change the direction, right? For example, there is a football, you kick it with your feet, it will go that direction, right? So you can change the direction using force. And one more thing, you can change shape. For example, you take some clay and you make a smiley face and you make two ears, right? What are you doing? You're changing the shape with the help of force. So these are the effects of force. The effects of forces are done. Now let us move on to okay, what is that? What is it given? Okay, nothing much important. Contact force and non-contact force. We'll just learn about contact and non-contact force, and we'll go to second law of motion. Okay, ouch, sorry. Contact force and non-contact force. For example, there is a ball here. Now the ball will fall down. Why will it fall down? Because of gravity. We know that ball will obviously fall due to gravity, right? So is it a contact force? Is there any contact between the ball and the ground? No. So it is a non-contact force. Okay, it's a non-contact force. Even magnetic force, this is a magnet and this is a this is a magnet and this is iron or something, some magnetic particle. It will be attracted. Is it a contact force? Is there any connection? No. So this is also a non-contact force. Then what are contact forces? What are contact forces? Friction is an example of a contact force because it has to be in contact. So what is friction? Basically, see, this is the floor. If you zoom the floor, this is how the floor look like, and the ball will kind of look like this. So the ends are like, stucking against each other. I mean, they're capturing the space. That is why it's difficult to move a ball. I mean, it's not difficult to move this ball, but what if the ball was heavier? So it has more friction, right? So it's difficult to move a heavy ball. So we learned friction is a contact force. Okay. Even muscular force. Even muscular force is a contact force, right? Muscular force is also a contact force. Is it right or not? It is a contact force. Okay. Now we are moving on to Newton's second law. Newton's second law. Okay. Now we're coming to momentum, basically the product of mass and velocity, right? That determines the force. Basically, it's difficult to catch a cricket ball because it has more mass, right? And also more velocity sometimes. So basically, the force that the cricket ball has on your hand is more, right? That's why it hurts whenever you. Or what if you're standing in volleyball practice? That happened to me and my friend one day. Okay, we were standing in volleyball practice and a ball came heading towards us, but thankfully it did not hit us. Okay, so this ball will have more force, right? If it hits someone, they'll feel very hurt. Why? Because it has more mass. Okay, mass, it has more even velocity, right? So that was just an example. Okay, that was just an example. So now basically from this and also see, if you apply the same force on two different bodies of different masses, this is a light body, this is a heavy body, which will acquire more speed? Obviously the light body, right? So if there is a feather and if you drop it from a height, and if there is a stone and if you drop it, or if you throw it, you're applying some force. If you throw it, which will fall faster? This one. Not because of the mass, I mean because of the mass as well, but here there is air resistance. Okay, fine, so let's just ignore the air resistance. And so from this example, we understand Newton's second law of motion, which is saying that the rate of change of momentum is directly proportional to the applied force, right? The rate of change of momentum, right? The rate of change of momentum is directly proportional to the force. The rate of change of momentum is directly proportional to the force and takes place in the direction in which force acts, right? Always momentum is in the direction of force. Okay, done. This is Newton's second law, and we'll just learn mathematical derivation of the second law. Okay, mathematical, we'll just write it down. Mathematical what is that? Derivation of second law. Second law. It's pretty simple. Okay, pretty simple.